So in the talk today, we are going to tackle two problems using ZK recursion. So the first is the high cost of ZK verification on EVM. The second is the long proving time for large ZK circuits. So let's see two examples. Our company, Polymer Labs, is working on ZK-IBC, and for both ZK-IBC or ZK bridge requires continuous verification of ZK light circuits on EVM. And currently, the cheapest ZK stock verification takes around 230K gas per proof. And if we assume the gas price 25 and the ETH price 1,600, then the cost per verification is around $9. And if we want to achieve a good user experience, we need, like, for example, 30 seconds per verification. Then the yearly cost becomes around 10 million. So the question is, can we share the cost with many users while still keeping the low latency? Another problem is the long proving time. Some background on the light client. So light client checks the consensus state of a blockchain, and on-chain light client verification enables communication between different blockchains without relying on a trusted third party. And for example, the Tendermint light client, typically we need 32 top ED255 Lightning signatures to be verified to reach the consensus. And if we use ED255 Lightning circuit, it takes about 12 seconds to prove a signature. So if we want to verify 32 signatures, it requires more than 6 minutes. And that's too long for our use case. So the question is, can we reduce the proving time still with the same amount of gas? We are going to solve this problem in using recursive ZK, but let's see some definitions. So this is a typical non-interactive ZK proof system. The prover takes public input X, waitlist or private input W, and produce the proof pi. Verifier takes public input X and the waitlist to generate true or false. In recursive ZKP, a new prover, here prover prime is added. It takes the X and the old proof pi as input and produce a new proof pi prime. And if the verifier verifies the new proof pi prime, then both the old proof pi and the new proof pi prime are verified. And there are commonly two types of recursive ZKP. First is recursively prove one ZKP inside one, and the second is recursively prove multiple ZKPs inside one, and they have different use cases. For example, the first one can be used to compress the proof size, and also can be used as incremental proofs. The second one can be used to aggregate proofs. It is used in the Mina and also the ZK EVMs to handing off the computation. Our contribution in this project, first we introduced the zkTree structure, which enables efficient aggregation of a large number of user proofs into one root proof, allowing users to share the constant cost of on-chain verification. And second, we prototyped the zkTree recursive proving pipeline using Plunky 2 and significantly improved the approval time. Third, we demonstrated the practical application of zkTree by verifying ten-domain consensus in a single proof on EVM. So in zkTree, there are 3 types of proofs. The first is user proof. It can be produced by any ZK protocols, such as Plunky2, Groth16. Currently, we are working on the support of pairings. So we will support Groth16 and Plunk. The leaf proof is used to recursively prove the user proofs and produce a standard zkTree proof that can be verified in a zkTree load proof. The load proof is the main type of proof that is used to build the zkTree. Both zkTree leaf proof and the load proof are implemented in Plunky2. So this is an example of a zkTree with 4 user proofs. And when building the leaf proof and the load proof, we will not only recursively prove the child proofs, we also calculate the input hash and the circuit hash of the user proofs so that we can build 2 merkle trees of the input hash and the circuit hash. With these 2 merkle roots, we can run the membership proof of. For example, if we want to prove user proof 4 is included in the root proof load 3, we can supply the merkle path, which includes the input hash, circuit hash of load 1, leaf 3, and user proof 4. We implemented zkTree using Plunky2, which has very fast recursion speed. It takes about 1 second to build a zkTree load proof. But it's very expensive to verify on EVM because it's based on Fry, which has large proof size. So we added a recursive proof here to recursively prove Plunky2 into a Groth16. So the proof size reduced from 130 KB to 200 bytes. The recursion time takes about 55 seconds. We also prototyped the distributed proof generation pipeline. In zkTree, the ZK proofs generation at the same level are independent. There's low communication cost. And in theory, the zkTree generation time is log n multiplied the proving time per load, so which is 1 second. The total communication cost is squared multiply the proof size, which is around 130K. The ingestion pipeline is very flexible. For example, we can customize the load distribution based on workers' hardware configurations. We can make it a data stream engine to make it possible for immediate inclusion of high priority user proofs. In this case, we will locate a balanced bilateral tree in this case. And for the final Groth16 circuit, it can be split into multiple sub-circuits with the trade-off between the prover speed and on-chain verification cost. So this is the result of our current pipeline. It takes about 17 seconds to generate each ED2519 proof in Plunky2. The zkTree generation time is 5 seconds. The rest is the recursion, Groth16 recursion. And total time around 77 seconds with 320K gas cost. And the time with the star mark can be reduced by split the circuits. In this case, we will get higher on-chain gas cost because we will deploy like multiple on-chain verifier. But we can reduce the total time to around 30 seconds. And also remember that we can distribute the gas cost among multiple users. So we can still like verify it at a very low cost. So that's it. We open sourced most of the code, and they are available here. And you can find more implementation details and more results in our ZKP paper. Thank you.
That's great. I think we do have a few minutes if there are any questions. Just put your hand up if you have a question about this, ZKTree. Doesn't look like there are any. So thanks so much.
Thank you.
Cheers.